Hi everyone, I'm Ian. It's a pleasure to electronically meet you. I'm really sorry I can't be there. I hope you're having a wonderful CAMRIA opening day. I unfortunately am running biostatistics exams today, so I can't make it. But I thought I'd make my face known and tell you a little bit about one of our exciting funded projects, HyperEvol, in which we'll be using tools from mathematical and computational modelling to understand the evolution of multi-drug resistance in pathogens. So the motivating question here, of course, we're all quite aware that antimicrobial resistance is a huge and developing problem as pathogens develop resistance to more and more of our drugs. But an essential scientific mystery here is the evolutionary pathways by which they develop that resistance. So a pathogen starts off without resistance to any human-designed drugs. Then does it first acquire resistance to drug A and then drug B? Is there something about acquiring resistance to drug B that makes drug C more likely to be evolved next? And so on and so on. And so what HyperEvol aims to do is learn these pathways of the evolution of antimicrobial resistance in a few key pathogens. I thought I'd give you a bit of an overview of the sort of approach we'll take, but I'm slightly limited in access to technology here. So we're going to try a bit of a Bob Dylan style slide presentation. Bear with me, let's see if this works. First slide, here is a pathogen that has no antimicrobial resistance. It is a point in a particular space, which I'll talk about in a minute, and it's got 3 dashes, meaning out of my 3 drugs that I'm considering here, it hasn't got resistance to any of them. Now, what happens as this bug evolves? It can do one of 3 things given these 3 drugs. It can evolve resistance to drug A, it can evolve resistance to drug B, or it can evolve resistance to drug C. Each of these is an evolutionary step that this pathogen might take. So we've got one set of states that a pathogen can be in where it has evolved resistance to one of our drugs. What happens next? Evolution is an ongoing process, so let's focus first on that bug that evolved resistance to drug A. It can now do one of 2 other things. Starting here, resistant to drug A only, it can evolve resistance to drug B as well, or it can evolve resistance to drug C as well. And if you follow through the different options that these pathogens have as they evolve various patterns of resistance, you'll see that all the next steps, given just 3 drugs, can be placed on a space like this. So we're starting again with a pathogen with no resistance profile, evolving resistance to drug A or B or C first, and then one of the follow-up resistance patterns through one of these other evolutionary transitions. And this gives us an overall evolutionary space that looks like a cube, starting from resistance to no drugs all the way over to resistance to all drugs through these various pathways that we could take as a pathogen evolving. Now, this is just a model. We mathematicians love building models, but this is quite a useful one because we can combine this model with various forms of data that exist in the world. For example, we can take samples of bacteria in some country, some hospital, some sampling regime, and we can look at their resistance profiles. We can ask which drugs are these pathogens resistant to. And we might see some data, for example, that I've represented like this. Here's my data. My drug resistance patterns involve the drugs A, B and C. Here I've seen one pathogen that is resistant to A only, and here I've seen another one that is resistant to A and B together. If I combine those data with my model using a process that we call parametric inference, we start to learn things about the likely structures of this model given what we see in the real world. So given these observed patterns of drug resistance, we might infer that this transition from no resistance to resistant to drug A is a very likely step. So I've given him a more weighted arrow. Then going from A to both A and B is also quite a likely step. So I colour in this arrow quite dark. Another thing that we could expect is not in exclusivity with this, but in tandem with this, we could have some bugs that evolve resistance to drug B first and then to A and B. So that would explain this data, but not this. And so we colour in those arrows a little bit. This gives us numbers in our model, which we can then use to go ahead and make predictions about what might happen next. This is a very derived case, of course. This just involves 3 drugs. In reality, we're in a position that's slightly harder for me to draw, but easy for a computer. This is kind of more like what we see. Here is a real data set published in Nature Genetics a few years ago about drug-resistant genes in tuberculosis in 1,000 Russian isolates. So each column here is a gene, and each row is a bacterium that has that particular gene, if it's coloured in black, associated with antimicrobial resistance. And just as we did on the previous page, we can take these data and use them to learn the structure of this now hypercubic model. We've gone from a cube to a hypercube as we have more features to take into account. But the principles remain the same, and then we can ask some interesting questions, having learned the structure of that hypercube, about, for example, if I'm a bacterium here, what is likely to happen next? What gene am I likely to acquire, or what drug am I likely to acquire resistance to next? Maybe learning the structure of this hypercube from these data suggests that this particular evolutionary transition is very likely, very coloured in arrow here. So if I now go to the clinic and I see a new pathogen with this profile, maybe I'll make a strong prediction that this is the next most likely thing to happen, and I'll design a treatment accordingly, avoiding the use of this drug, which is most likely to be evolved resistance to next. Bob Dylan over. I'll just summarise with a few bits and bobs about the project. So this is in collaboration with several folks both around Norway at Stavanger University Hospital and here in Bergen. It's also in collaboration with the Institute of Microbiology and Infection in Birmingham. So we've got a nice international feel. And the project is broadly put into three parts. One is developing this machinery to link the data with the models, as I've just discussed. Another is applying that newly developed machinery to learn about the evolution of antimicrobial resistance in Klebsiella and tuberculosis and several other pathogens of interest. We're doing this both from data in Norway, new data from our collaborators and existing data that's already out there. We're also going to take a look at some African data. We have several connections with Tanzania in the PI set. So we're going to do a comparison of the evolutionary pathways that we learn in Norway and Tanzania to see if there are geographical differences in how these bugs evolve resistance. And finally, an important part of the project is making the associated software fast, free, easy to use, and totally available, so that clinicians all over the world can input their profiles, their observed profiles of drug resistance, and learn about what is most likely to happen next and design clinical therapies and treatments accordingly. So that's the overview. I'd be delighted to talk more about this, so please reach out if you have any further questions or comments. I hope you have a wonderful rest of the opening day. Apologies again for not making it, and I look forward to meeting you in reality sometime soon. Thanks for your time. Bye.